So my talk is on estimating reaction rates from models of variable density turbulent flow. Uh, More generally, the question is, suppose you're simulating uh, a fluid with averaged models which propagate certain moments, but what you're interested in involves a different moment. Uh, what do you do about that? And the particular instance that I'm looking at here is variable density turbulent flow, where you have two incompressible fluids, and the density variations then are just due to the changes in composition. But the important thing is that this ratio in the densities might be large. Um, so um, the flow is turbulent, so we're using averaged equations, and the ones that I'm familiar with are the BHR equations. Um, And if you do the averaging, and this is true, I think, in other models, not just the BHR model, but what comes out when you just look at the moments involving only the density is you get two moments. One is the mean density, and the other is this quantity called B. They call it B. I wish there was a more I tried calling it the buoyancy coefficient when I talked about this somewhere else, and then people told me, "Oh no, that's something different." So we'll just have to call it B. But B is the negative covariance of the density and 1 over the density or the specific volume. And the interesting thing about this is that when you average these equations, the variance does not arise. And that's something that we're accustomed to handling, and it has very nice properties, but it doesn't come up in the averaging, except as an approximation. And the approximation is only valid for small fluctuations. B has some of the same properties as the variance in the sense that it's always positive, and it goes to zero when the fluctuations go to zero. But it's clearly a different beast. So in some flows, we might also be interested in a reaction taking place in the flow. The fluids may react with each other, or one may react with itself. And this reaction rate frequently depends on the variance of the density. And here is a very kind of schematic representation, but this is the reaction rate is equal to some constant times 1 minus the variance over the maximum variance. And this is a problem that actually comes up in inertial confinement. Propagating these other moments, B and rho bar, but in order to determine the reaction rate, you need the variance. How can you get from what you have to what you need? Um, okay, yeah, this is kind of what I just said here. We know B and rho. How do we determine the reaction rate and sigma squared? And also, what is if we just estimate a fixed value for sigma squared, what is the uncertainty in that estimate? And how does this uncertainty depend on the density variation, or more specifically in this model, on the ratio between the densities of the two fluids? So the previous efforts, so far as I can tell, I mean, this is a recognized problem in the literature. The previous efforts, there's a couple of different classes. One is to expand in fluctuations, and the term there over on the right is the remainder term. You can actually calculate that for simple distributions, and it sometimes diverges. So as you add more and more terms, your approximation gets worse and worse. It's really only you, and you see if you look at the first term, that's the variance up top. Rho prime is just rho minus rho bar. So if you have a small fluctuation, then working with B and working with the variance is basically equivalent, but it's only useful when the differences between the densities are pretty small. And I measure it with this little small r, which goes to zero when rho 2 and rho 1 are the same. A second approach is to use closure approximations. And I've written out just kind of the general idea here. You would write sigma squared on the left, and on the right, you want to have an expression that just involves B and rho bar. And this is just a mathematical identity, actually. And it involves a couple of moments. One is the skewness, the third order moment. And then that moment way over there on the right is a fourth order moment. And these are closed in terms of B and rho bar, and that gives you your closure approximation. So this has a couple of weaknesses. One is that it doesn't provide uncertainty estimates. It allows you to get an estimate of, the reaction rate if you want, but you don't know how much uncertainty there is. And it's not really clear that it's realizable in the sense that is there any distribution that could lead to this variance? And it turns out that when I did, I'm getting ahead of myself, but when I did get the bounds, I plugged this in and I realized it isn't actually realizable. And the reason is that the different distributions were used to estimate the skewness and this fourth order term. And so there's no guarantee that any single distribution is going to give this estimate for sigma squared. And it turns out that it can be quite incorrect. But this is what's in the literature now for a closure approximation for sigma squared. So moving on then, looking for another approach, I'll just give the result that I've derived, and then I'll go on and show how to derive it. But you can actually use moment methods to provide exact bounds for sigma squared in terms of B and rho bar. It may look like the bounds depend on this V bar thing, the mean of the specific volume, but that is actually simply expressed in terms of B and rho bar. So those bounds on either side just depend on B and rho bar. And as I say, they're exact bounds. You can find distributions that achieve both the upper and lower bounds. So without further assumptions, you can't improve on these bounds. Given these formulas, you can evaluate how this depends on the this R quantity, which is how unequal these densities are. And as I'll show below, the bounds actually get pretty large. You have a lot of uncertainty when R is large. And then you can also get from this approach, if you want to have a single value that you can use, you can get a closure just by taking the geometric mean of the upper and lower bounds. And this is guaranteed to be realizable because it's in that range. So moving on, the moment methods, the way they come up, V can actually be written in many different ways. And the usual approach is this negative covariance of rho prime and V prime. But if you just plug in rho minus rho bar and the same for V, you get this other expression, mean of rho, mean of V minus 1. And the third one I'm not going to discuss in this talk, but it's actually just kind of striking to me that if you go to the mass averaging, you can actually express V in terms of a variance, and that might have some potential for modeling. But at any rate, we use the second expression because we're looking, that reduces it to two kind of first order, to two moments. And you can see that knowing B and rho bar is equivalent to knowing rho bar and V bar. In other words, knowing the moments of order 1 and minus 1. So our problem of bounding sigma squared in terms of B and rho bar is equivalent to the problem of bounding a moment of order 2 in terms of the moments of order 1 and minus 1. And this is a generalized Chebyshev problem. The Chebyshev problems involve, if you know some moments, what can you say about other moments? And these bounds tend to be weak, but their advantage is that they don't make any distributional assumptions. So the problem was posed by Chebyshev, and it was solved for these classical monomial moments by Markov in his PhD thesis back in 1884, using a rather beautiful but complex formalism of continued fractions. As things developed, Kara-Theodori recognized that methods of convexity could be used, and it replaced this complicated approach through continued fractions. And there's actually a number of approaches to this problem. It was a very fertile area of research. But finally, in the 1950s, Mark Krein and Sam Carlin came up with a method generalizing this to Chebyshev systems. And the point of all these generalizations is that the moment functions don't have to be these classical monomials with positive exponents. They can actually be quite general. And so I'm just going to say a couple of things about the formalism. So this is I hesitate putting this slide up because, but this is basically because it's a bit complicated. But this is basically the if you have moment functions u sub I, and you know the moments for I is from 1 to n, and you want to bound this generalized moment n plus 1, then you can do it as long as this condition is satisfied that this determinant, you take values of in your interval t1 through tn, this would be rho in our example, and so that they're increasing, and you look at this determinant, and if it's greater than 0 for all values of t1 and tn, then you say it's a Chebyshev system. And so this gets you out of just having to use monomials. If you do use monomials, this is a van der Moon matrix, and you can just write down the determinant, and that's patently positive. So, and then in order to derive the bounds, we require that both u1 through un and u1 through un plus 1 are Chebyshev systems. So that's the main. It may look like, I mean, when I first saw this, I thought, how often is that going to happen that thing stays greater than 0? But if u1 and un are independent, then it can't be exactly 0, and this is a connected domain, so it can't pass from one sign to the other. So it's actually a very broad generalization of the classical theory on monomials. And with this system, the extremal values are given by sums of point measures, which is another kind of salient point about the method. So without going through the technicalities, let me try to give a kind of a graphical explanation of how this works. Here you have something where you have the rho on the x-axis and 1 over rho on the y-axis, and then you have a moment. You have moments for each of these, generalized moments for rho and generalized moments for 1 over rho, and that's, you might have a point P there. And so what you do is this blue line is actually the moments you would get if you just took point measures at every point between rho 1 and rho 2. And what Kara Theodori pointed out was that the whole space of possible moments for both of these is this shaded region. It's the convex hull of this blue line, and that's a general result. So if you know what your moments are given by, and so this point P has to be in this shaded region. If you know what your moments are and you have a point P there, you can actually achieve that with a wide variety of measures, like basically an infinite number of different measures. But there are a couple that are special. And one is where you point a point mass on rho 1, and a point, you draw a line from this point A to the point through the point P, and it intersects this blue line at point C, and you put a point mass at rho 1 and a point mass at psi, and you weight them so that the expectation of rho and V is what you've got. And so that's one measure. Then the other thing you can do is you can start with a similar measure by drawing a line between D and B. And so you have these two kind of special measures. They're both sums of point measures. And those measures actually give you the extremal values. So if you're interested in another generalized moment, you just evaluate that generalized moment with respect to these point measures. And Okay, so if we look at how this works here's my attempt to render it in 3 dimensions. So if you project this down on the plane, you get exactly what I showed on the previous graph. But we want to find the bounds for this other functional that's going in the z direction. And so what the previous result said is, and here again, this blue line is just the line you get from the point measures. And the convex hull of that is the space of possible measures. And if we want to look at the minimum and the maximum, we just find a point on the plane there and draw a line up. And where it punctures the bottom surface, that's the minimum. And when it emerges on the other side from the top surface, that's the maximum. Okay, so I hope that was that was helpful in explaining it. It's better than going through all the equations, but anyway, so when I do this, in order to show the results, it's easiest to express this in terms of normalized quantities. Now, R isn't normalized. That's the thing that I showed you before that just quantifies how different these densities are. But S is the normalized mean density. So this goes from 0 to 1. I sub B, which is also called the intensity sometimes, is the normalized B compared to the maximum value for a given value of rho bar. And I sub sigma squared is the same thing for sigma squared. So if we look then at the bounds for this normalized sigma squared, given the normalized B, at S equals 1/2. So S equals 1/2 is where the mean density is just halfway between the lower density and the upper density. It's rho 1 plus rho 2 over 2. And so, and then we can look at these bands around the diagonal. The diagonal is if basically we could tell sigma squared directly from the value of B. So if R is equal to 1, that's the red line. And so we take a certain value of B and we can look at the uncertainty, how big the band is there for the red lines. If it increases to 4, which corresponds to a density ratio of 5, then it's the green lines. And as this ratio gets larger, we see that the control over sigma squared gets less and less. So we have more and more uncertainty as to what sigma squared is. So so that's the result for a fixed value of S. The other thing we can do is we can plot this for a fixed value of R. So R equals 9. That means that we're looking at density ratios of 10. And now if you plot normalized B and normalized S on the horizontal axis, then the lower surface here is the lower bound, and the upper surface is the upper bound, and the blue surface is the closure that I gave before, the harmonic mean of the two. So you can see how much uncertainty there is in sigma squared. So so that's basically it. So this problem of estimating sigma squared and the reaction rates from what you get out of the simulations in terms of B and rho bar was it was recognized as being a problem, but there weren't really any satisfactory solutions for it. But by using these moment methods, we get some exact bounds. I haven't gone into it, but the methods are quite general, and you can add in other constraints and stuff. For example, you can constrain the distribution to have a single hump, and that wouldn't be appropriate for this particular problem, but it might be useful in some other problems. So this is just one simple application of these methods. The other thing that can be useful about this is that if you're doing a computer simulation, you can check and make sure that it's staying within these bounds, and if it isn't, then you know that there's a problem. So, at any rate, that's all I had to say. So, thank you very much.
Other questions for the speaker? Yes.
Yes, that was a very interesting talk. The solution is highly mathematical. I was wondering if this has been put to any practical use, or how it would work out if it was tried to be used in practice.
To my knowledge, it hasn't been used in practice at this point. And your point that it's highly mathematical is completely correct. There's a lot of idealizations here. For example, if you look at this reaction rate, for example, in a real problem, this coefficient K is going to depend on temperature. And if you have a reaction going, then it's going to change. So there's a lot of issues that come up in applying this to a practical problem. Um, I think the main point here is that it does give you some mathematical control, and the alternative is just to use these closure approximations, and so I think, yeah, so at any rate, I mean, it's a good point. It has a ways to go before it can be applied to real problems.
Any other questions? Okay, let's thank our speaker again.